So in this video, this is going to be quite a lengthy one, but we're going to be talking about carbon nucleophiles today. Now there's many of them. There's the Wittig reagent, that's going to make alkene additions. Then we have Baeyer-Villiger, that will be an interesting reaction, that uses peroxy-acids. Then we're also going to be looking at the Grignard reagent. We'll also look at cyanohydrin formation. So 4 reactions we're covering today. We're going to begin with what we call the Wittig. Now we take a ketone and we turn it into a double bond carbon. So we kind of replace the oxygen with a carbon here, and it's 2 hydrogens. Now you could add R groups to these hydrogens instead. You could make this, say, a butyl group, or we could make this a methyl or an ethyl group, say. So the Wittig, you add carbon groups, but you add alkenes to it. So kind of synthetically useful, I'd say. And the reagents to do this is called, you need to use a ylide ion, which looks like this. So we're gonna have a whatever carbon group we want to attach. So we'll call this R, and then we're gonna have a double bond. And then we're going to have a phosphorus, and then 3 phenyl rings, which I'll call pH. And that's it. You only need the ylide. What is a ylide? Now, I want to formally explain this to you. A ylide looks, again, like this. I'm kind of just blowing up what this is. So this is a ylide. Now, the phosphorus carbon bond that we see here, carbon to phosphorus, is very weak. This is the dipole diagram, right? So the carbon is feeling exceptionally negative, and what this causes is a resonance form to attribute where phosphorus has a positive charge and this carbon has a negative charge. So when it attacks a ketone, what it does is it's going to reach out, kind of like our hydride delivery agent, is going to attack the carbonyl. This in turn is going to cause this bond to reach out and attack the phosphorus's positive charge. It's like a double nucleophilic attack. And you get this really interesting intermediate when you do this, and this is what you need to know. So we're going to have, and I'm going to push this bond down a little bit. But we'll have the oxygen carbon bond, then we're going to have the carbon to the R groups, okay, and then the rest of the molecule, and then this is this carbon here, which is connected to the phosphorus, not R, phosphorus, P. And then this oxygen is connected to the phosphorus. So it makes kind of a 4-membered little ring here, okay? So I hope you can see it. And it goes to this ring, and this ring is unstable. A 4-membered ring is like, I don't want to exist. Nope, Angle strain, 90 degrees, hell no. So what happens is these electrons are going to fold in. These electrons are going to fold out, and we're going to get a product here. So we're going to have this group leave as this. So we have, it's kind of like our ylide, but we replace the carbon with that oxygen. So it kind of takes the carbonyl with it, and it's going to form this group here. All right, so pretty simple. It just adds R groups, and then it also makes an alkene. So pretty simple reaction. You need to know this mechanism, that it first attacks and then pushes out and attacks the phosphorus. You'll either see it with the double bond or you'll see it with the plus and minus. If you see it with the double bond, draw it with the plus and minus charge. It will help you figure out the mechanism quite simple. It goes to this 4-membered ring intermediate, the box, we call it the box, and it collapses, and then you get your final product. So there's another note I want to make about the Wittig, and I'll actually write out how you spell that because that's kind of important, isn't it? The Wittig, W-I-T-T-G, Wittig. An important note is, how do we make Wittig reagents? Well, it's quite simple. So we're going to take some sort of carbon chain that we want to attach. What we do is we take phosphate triphenyl, I would assume that's how you say that, or triphenyl phosphate. I don't know, it's been a little bit. But the molecule's stable. The phosphorus comes in and kicks out the bromine to form kind of what we have, but not particularly, where we have the phosphorus phenyl attached to the carbon chain. What happens next is there's not a double bond there. There's a positive charge on the phosphorus. And now we need to use a really, really strong nucleophile, say like butyl lithium. A carbon with a negative charge is like hell on earth. So what happens is it's going to reach out really, really, really quick and make a double bond here. And thus we have a Wittig. So that's how we make Wittigs. We use the triphenyl phosphate, and then we use a really strong base like the butyl lithium. That's going to deprotonate, make a double bond, and then this Wittig reagent is ready for action. Okay, so we understand that. Pretty simple, I'd say. Now what I want to talk about is there's some selectivity of alkene, right? Are we going to make Z alkenes, or are we going to make E alkenes? Wittig will always make Z normally if you just have carbon chains. But if you have electron withdrawing groups on your Wittig, you're going to get E. Okay, so if I have this ketone here, and I want to add, and I'm going to add this to the thing. This group is more priority than this group. So the Wittig, let's say we have we got to be more specific here with our reagent because we need to make Z. Let's just say we have one R group. Right? And there's no electron withdrawing group on there. Well, like I just said, we're going to get the Z here, so we're going to make the double bond, but when we predict our products, it needs to be on the same side. Z means on the same side of the alkene, and for a Wittig with no withdrawing group on the ylide, it's just going to make a Z. Let's say on this R group, I put a carbon chain that doesn't look really good, does it? And I put an electron withdrawing group. Let's do this one. Let's put it here. Yeah, right here is fine. So we put an electron withdrawing group right on the ylide. What do you think is going to happen? Well, instead of being Z configured, it's going to flip to be E configured. And that means that this needs to go the other way. So it just flips. Pretty simple. So that's the Wittig. So some important notes. The ylide is needed. You need to know the mechanism, and you also need to know whether it makes a Z or E configured alkene product. So that's the Wittig. Next, what I want to talk about is called the Baeyer-Villiger reaction. This is going to be a lengthy one as well. So it begins quite simply. We just need to use a peroxy-acid. So let's use MCPBA. Probably the most common peroxy-acid that you've seen. That's going to look like this, HOO carbonyl phenyl ring. Hopefully you've seen MCPBA before, but if not, now you have. What it's going to create is we're going to notice this is going to happen. Usually we used MCPBA to make epoxides, right? But here it's a little different. We now make esters. That's very synthetically useful to make an ester from a ketone. What I want to talk about next is called a Baeyer-Villiger oxidation. Now, I'm going to write out what that actually, how that's spelled out, because it is a little interesting. Like people say Baeyer-Villiger, or not, well, that would be correct. Baeyer-Villiger, it's Baeyer-Villiger. Baeyer-Villiger, not Villager. People have been playing a little too much Minecraft, I suppose. It's called the Baeyer-Villiger oxidation, and basically we take MCPBA, or any peroxy acid for that matter, react it with a ketone, and what we see happen is we get this here, right? So if we did Baeyer-Villiger oxidation of acetone, we'd get an ester that looks like that, for example. Now there's an important note that I want to make with the Baeyer-Villiger oxidation, and that's we need to identify what's called the migratory amplitude of this reaction. Now we're going to find out that for a Baeyer-Villiger oxidation, it's going to do it most if it has to pick on one side, because notice here we have a symmetrical ketone, right? There's both a primary carbon here and a primary carbon here. But let's say, for example, and to better get my point across, I'll give you an example. Which side will the peroxy acid, and I'll just write PA for peroxy acid here. Which side will the peroxy acid pick? Well, what it turns out is it will pick the hydrogen, okay? And we'll actually explain why. And you'll get a carboxylic acid. There's a migratory amplitude, and basically what that says is, okay, if I have to pick, if I'm a stinky little peroxy acid, which side of the ketone will I pick? That's basically migratory amplitude. And what it will say is, I'm going to pick a hydrogen, but if I don't have a hydrogen, I'll take a tertiary. If I don't have a tertiary, I'll take a secondary or a phenyl. But if I don't have that, I'll take a primary. So basically, what this says is, if it has to pick, it's going to pick a hydrogen over a tertiary, over a secondary, or a phenyl. But if it really has to, it will pick a primary, like up there with acetone. With the hydrogen, it will never pick the primary side almost ever. It's always going to want to go there. So hopefully that makes sense there. But now we need to actually get into the mechanism of this reaction, which can get kind of dicey. So, so now for a mechanism, how does this actually happen? Let's do the acetone example. So when this reacts with the peroxy acid, the first step is that this oxygen here with the hydrogen is like, hello, Mr. Ketone, I want to make myself at home. Let me on in. So he does that. He's like, he sits his fat ass on the couch and he's like, oh yes, I finally made it into this house. I've been wanting to be here for my whole life. I don't know, I'm just a chemistry person, Brett. Some basic species will come in and deprotonate. So we'll say ROH is going to come in and steal a proton and help the peroxy acid make himself at home. He basically, hydrogen is his shoes. He's going to take his shoes. I'm trying to take off my shoe. He's going to, I just threw my shoe at the door. So now I'm doing this in my socks, but that's okay. He kicks off his shoes and he makes himself at home. So we have this molecule here. The oxygen finally realizes this stranger's on his couch, so he's like, peroxy acid, get out of my house. What are you doing? He's going to be like, get out. So he kicks his electrons out. He's like, basically pulls out a gun. He's like, God damn it, get out of my house. Peroxy acid's like, I don't want to go. He doesn't want to budge. He doesn't have a reason to. He's not protonated. If he was up here, if the oxygen caught him up here, he'd be like, okay, get out. And peroxy acid would be like, oh crap, I got my shoes on. I can run. He doesn't have his shoes on. He's barefoot. He's like, oh crap, I can't run. Well, I'm cooked. But carbon comes in to save the day. Basically, he says, I'll take you in. And the rest of the peroxy acid, his little buddy here, is going to leave as well. So what we get is this here. We also get a carboxylate. which is this group here. So not only do we get a carboxylate, we get our product in question here, our ester. Hopefully what I said has made sense. This mechanism is kind of interesting. I like to think of it more as that story of the peroxy-acid makes itself at home. I think it's a great way to look at it. Thus the Baeyer-Villiger. Remember, do not forget that migratory amplitude. Oh my goodness, the amount of times I see on exams or how people answer questions, it's like they do it the wrong way and it kills me. Migratory amplitude, it's hydrogen, most bulky to least bulky. So yeah, that's the Baeyer-Villiger. There's two more reactions that we have to talk about. That's going to be cyanohydrin formation. And along with cyanohydrin formation, we're also going to talk about the Grignard reagent, which you've probably seen before. So a Grignard looks like this. Okay, it's kind of interesting how we make it. Let's say we want to make an ethyl or a propyl Grignard. What we do is we react magnesium, and we need an alkyl halide to start. So we have some sort of alkyl halide, and we're going to use magnesium metal and diethyl ether. And what's going to happen is this magnesium is going to butt his way in to the alkyl halide. So he sandwiches his way into that bond, and it actually goes through a radical process. I'll actually go ahead and show you that, because it's kind of a cool mechanism that not a lot of teachers show. We have our alkyl halide, and we have the magnesium. Magnesium metal has 2 valence electrons, and it's ready to give them up. So what happens first is he homolytically cleaves the bond and puts a radical onto this carbon here. So we have a radical carbon, and we have a radical magnesium bromine. So what happens next is we're just going to get termination step, and that's where we get the Grignard. Properties of Grignards. Properties of Grignards. Now, I'm going to draw just a generic Grignard here, with the bond from the carbon to the magnesium elaborated. Magnesium is a group 1 metal. Carbon is on the whole other side of the periodic table. We would assume ionic. It is so close to ionic. It's not ionic. It's a covalent bond, but it's so close to ionic, we could basically consider this a full negative charge and this a full positive charge. Basically, it's just under the threshold by a little bit. Right, it's feeling negative. So treat the R group directly off of the magnesium as being a negative charge, aka a nucleophile. So let's say we have this Grignard reagent here. So we have H3 and a methyl MgBr. Okay, so this is our Grignard reagent. If I say that this is almost negative, it's not negative. Do not put negative on your final form of the exam. You have to show it from the bond, but let's treat carbon as negative. What happens is this bond is going to do backside attack on that carbonyl, and it's going to kick up electrons. He says, I'm making my way at home. Magnesium bromine bond breaks and just leaves as magnesium bromine. What happens next is we have oxygen with a negative charge, and we have our methyl group here. So the Grignard is going to make himself at home here. Now he doesn't want to leave. This oxygen just can't kick him out. So what needs to happen next is just an acid workup. We use an acid in a second step by itself. It needs to be 2 distinct steps, because the Grignard with a negative charge on a carbon, he's going to see a hydrogen and just eat him like Pac-Man. So we just have an acid workup step separate from when we did our Grignard, and we get alcohol. In this case, we got a tertiary alcohol, and we added a carbon group. So that's the Grignard reagent. Now we need to talk about cyanohydrin formation. Kind of a long video, but we're almost done here. When I talk about cyanohydrin, I'm talking about adding this. So we have a cyano group and a hydroxyl group. Cyanohydrin. Hydrin meaning hydroxyl, cyano meaning cyanide. So how do we do this? Well, we need to use a group 1 metal, KCN, with the corresponding hydrogen cyanide. So this is base catalyzed nucleophilic attack. So it's pretty simple actually how this works. The CN is acting as like a supporting ion to help drive the equilibrium. The H will just be a source of protons, but this is a group 1 ionic species, potassium cyanide. So the cyanide comes in with its negative charge and kicks up electrons, makes himself at home. We have the cyanide. It's not going to go anywhere after this. He made himself at home and he's not going to move. That means that the oxygen just can't kick him out. So that's where HCN comes in and protonates, and thus a cyanohydrin. This is a very interesting reagent because then we can go ahead and do chemistry with the cyano group, which we'll cover in a later video when we get to nitrogen nucleophiles or carboxylic acid chemistry. We can hydrolyze that into a carboxylic acid, for example, or we can make an amine from that if we use, I believe, lithium aluminum hydride and acid, for example. So there's a lot of applications to adding cyano groups to this. We can also get rid of the OH and just make it a cyanide group. There's a lot of practical applications to this, but it's good to get an introduction here so you know the reaction. Hope you guys enjoyed. If you did, please drop a like, subscribe, comment if you have any questions, and have a wonderful day. Boom, we're done.